Section. So the next presentation, I don't need to introduce the presenter. Alireza was the last presenter, and he's continuing to present. So please go ahead.
Oh yeah, I lost my cables here. Let me see. Oh, my cables. Yeah. So yeah. So let me start like previous one to tell you what I'm going to tell you. And this one you heard it a lot from many places. Dealing with temperature change is not easy, and we have to work together. That's all about this. We're saying changing the temperature in car is not an easy problem. We have to work together and make it easier. And I'm going to go through it and explain why this is the case. So this nothing new. The car we know that has to work in any situation, in high temperature, low temperature. This is not new. And for doing that, to make sure this is happening, we have a couple of tests we designed, the system people like us design to deal with it. One is a static test. When we are, and the way of doing the test, you put everything inside of oven, and then you put in the oven, go to the certain temperature, and you are hoping that things work very fine, everything works fine, error-free. This is going to be making sure when you are turning off your car on any temperature, any place in the world, the car is stopped. The second test we have is we have a temperature ramp. So the temperature, we start from one temperature, we go higher, lower, we stay there. Also, we have the same expectation. We want the car work in this changing the temperature. Essentially, this is to do, our hope here is that if we start from a very warm place, we go to the very cold place, we go up the mountain, we want the car working when it's moving up or moving down. That's the whole goal. So looking at this test, are well-defined tests in terms of doing. You put things in the oven, in the static test, for example, you put it there, you say, okay, if my cable is following the characteristic that explain the standard, I should be fine, I should make it done. So very clear objective, very clear setting, everything done. In the temperature ramp, the things is not that easy. And I hope to be able to communicate with you why it's not easy there. So again, doing the temperature ramp is easy to do, but getting good result is hard. And what I want to explain here, why it's hard to get. So first, what we're going to do. We are having this 15-meter cable. That's the limit line we have for some standard. We have the 4-line inline connector. We put the system inside the oven, and we measured. Say, what's going to happen minus 40 degree, 105 degree. See, what's the change we're going to see, and how are we going to handle it? Are we able to handle this problem? And obviously, the first thing we look is insertion loss of the cable. You see the insertion loss versus frequency. Same cable, and you can see that we have the one blue line here in the top, which is minus 40 degree. That cable, that's the insertion loss of the cable in minus 40 degree. Same cable, when you go to 105, we get this one. It's a purplish line here. This is going to be insertion loss of your cable. If you look at the number here, 2.5 gig, for example, this difference is about 8 dB. And 8 dB is a big number, you know. It means that your signal level can go up by 2.5 factor, 2.5. So the signal level is going to be more than become twice bigger by 2 times, or become smaller by 2 times when you change in the temperature in that particular frequency. It's obviously easier to do on a smaller frequency, but this is the range that we have to deal with it. If we want to have no error, we have to handle this one correctly. It can be done, yes, this can be done. It's not cheap. We need some system, but can be done. And the way we are doing it is we are doing some trick. We say, okay, the cable is going to change this much. Let's have some over design here. Let's have some margin in our analog front end. let's have some adaptation, faster adaptation. Let's make it done. So this means some hardware to do, to give you this margin, to do this adaptation faster. But this can be done. Next problem. So magnitude of signal is changing. You can see it here. The blue line is the same blue line before. Same cable, 15-meter cable. We show impulse response over the time. And you see the blue line here, which was 15-meter cable and minus 40 degrees. It's bigger, and it's going to get to you later, so it has more delay. So if you go to the 105 degree, you say less magnetic signal, and you're going to get it earlier. That difference between time, that same cable, high temperature, low temperature, that difference is about 0.3 nanoseconds. This is about 1.7 symbol of 10G base T. So that's the amount of the change that your cable causing in terms of sampling point. If you don't do anything about it, this sampling point is going to change this much. And we don't like to do that. We don't want this to happen. So again, we can't control it. We can't do something. We have to make the sampling time more controlled. So we have to have that one. We may have to do some adaptation here faster in equalizer. Maybe we have to do something in echo canceller also to make it faster. So if we spend power, we spend some area, we can solve that problem. Then we look at the echo return loss. And here you see the return loss over frequency. It is something that's different, right? The same phenomena playing there, but we know it's changing, but it's not a well trend that to explain here, so to summarize everything here. But the only thing I want you guys to pay attention that this graph is not the same when you're moving from one temperature to another one, and you have to handle it. To handle it, again, maybe you have to do some echo cancellation better, you have to do it in data mode. Also, you have to do some more work in your analog front end, in some design, depending on design. So, up to now, is hard. It's not easy engineering problem, but should be done, right? So we put some margin on design. We make a design based on the temperature. Yes, the signal level is going to be 2 times higher and lower in some frequency, but looks like can be handled. This is an engineering problem. The problem we have is that it's not enough. We can show that we still need some work, and we have to do this work through all of us that involved with automobile link. And problem here is that we are not getting the same response from the different brand of cables. So this is the result coming from 2 different cables, 15 meter, both the same. What we are showing here is the average gain over the temperature. The point of this presentation, forget about number, is that there's a 2 cable with 2 different response over the temperature. Now, become a question that how we should design the system. Should we over-design it? Yes, but how much over-design? What would be the best over-design? What does the over-design mean? How we can put this area, extra work for what? And then if we design less, then tomorrow we're going to be constrained over the cable selection. So we said, oh, no, guys, you cannot change your cable, although that you find a better cable somewhere, but you cannot use it because it has this problem, right? So what we are hoping here to get some guidance from all of the system, people from all levels in the system, and we come with some mean and max requirement, that what's going to happen in temperature ramp. So go farther in defining the test. So right now we said, put the system inside of oven, go from minus 40 to 105, that system. And now, tell us more. Tell us that what should happen in the cable. How much change should happen during this transition. Put the sum limit, because this is going to enable people to work better. This is going to be something that is shadow, and we are not talking about it, bring it top, but we talk about it. So we say that we have a cable, we use a different cable, it has this characteristic. So we shouldn't worry that if we change the cable here and there, we're going to see the behavior, different behavior. So that's the things that we are hoping for to get. And this is going to help us for other things. I mean, you heard two previous talks that concern about EMC, right? So now, think about it. One of the factors that I think was asking, say, hey, we have to define common mode to differential gain. We have to have some spec for it, right? That was a requirement. That was a request that we heard about it 2 talks ago. And the reason they want to put the limit, the reason that we want to define it, because this common mode become differential, that become noise is going to affect your system, right? And now imagine that you had this system, it's passing very nice in one temperature, is everything going fine. But then you change the temperature. Is it going to pass in new temperature? How we can putting some limit here can help us to pass that test or simplify that test? That's the question, how we should answer that question become issue. So, in the end, dealing with temperature ramp is not easy. Temperature changing is going to change a lot of things. We have to be careful about how we want to define the system and how far we want to be over-design the system, which direction we have to go, and maybe we need some more requirements, some more clarification here that what this temperature ramp mean in terms of the whole system. That's it. I'm ready for questions.
So thank you very much for your presentation. Are there some questions? Please, questions. No? I have to apologize. I also don't have a question for you.
No, it's fine. The temperature is changing. We have to deal with it, right?
Exactly.
Yeah.
All right. Thank you very much.
Thank you.